this video, I want to prove this following theorem. So the theorem is, let F be a field and let's say that P of X, let's say P of T is, suppose that P of T is an irreducible polynomial with coefficients in F, then there is a field E, which I think of as a field containing F, even though that's strictly speaking not true. There's a field E and an injective field homomorphism phi from F into E. So by using this homomorphism, we're thinking of F as elements of E. So there is a field E together with this injective field homomorphism such that, so when you have a polynomial with coefficients in F, you can think of it as having coefficients in E via this map phi, right? So such that P of T viewed as a polynomial in the polynomial ring of E has a root in E. So the idea is that, if you have a field and you just have a polynomial with coefficients in F, that might not have any roots in F. So for instance, if you take the field to be F equals R, the real numbers, then, if you just take x squared plus 1, right, that's a coefficient with polynomials in F, but it doesn't have any roots in F. But there's a field together with an embedding of F into that bigger field, such that when you view that polynomial in this bigger field, that polynomial has a root in this bigger field. Okay, that's the idea. So the proof goes as follows. So we have this construction where, okay, consider P of X. So let's say X is some indeterminate, and we consider P of X. Then we can consider the polynomial ideal generated by P of X in the polynomial ring F of X. Right? I'm using capital X. So this is an ideal, and this is in fact the maximal ideal inside this integral domain capital F of X. Right? Capital F of X is an integral domain. And so the quotient ring is actually a field. So this is a field. And this will be our E in the theorem. Right? This field E is a field E. Okay, now what's the map? We have to define a map phi from F into E. So we define a map phi from F into E, which is this polynomial quotient, by just the natural map. A maps to the coset. So okay, A plus this, right? So just a reminder that the elements of this set have their elements of the form g of x plus the ideal generated by p of x, right? I mean, it's what you get by taking the set of equivalence classes where the equivalence relation is that g of x and h of x are equivalent if their difference is in the ideal generated by p of x. And for simplicity, let's just denote this by this coset. Let's denote it by that. Okay, I think it makes it easier to understand what's going on. So in other words, phi of A is this coset containing A. Right? It's the equivalence class of A. Okay. Now, I claim that this is injective. So it's easy to check that this is a ring homomorphism, and it's injective because it takes, so notice that phi of 1 is not, okay, so the 0 element in this field, right, is the coset containing p of x. So, and phi of 1 is just equal to 1. Well, it's the coset containing 1, which is certainly not, 1 is not in the ideal generated by p of x, and so it is not the 0 element in E. So, and so this is a ring homomorphism whose domain is a field, and so phi is injective, right? I mean, the kernel is either all of f or it's 0, and we just showed that the kernel is not 0 because phi is not injective, and so what am I saying? Am I getting mixed up? No, I'm not getting mixed up. No, I'm not getting mixed up. Phi is in fact injective, and therefore phi is a field homomorphism, an injective field homomorphism. Okay, so now we have our map phi from F into E. That's good. Now we just need to show that this actually satisfies the hypotheses of the theorem. So we need to show that P of t, viewed as a polynomial in E of t, has a root in E. Okay, so P of t, let's write P of t as a0 plus a1t plus a2t squared plus dot 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 plus an t to the n. Then, so here, where the AIs are in F. Right, now we're viewing this as a polynomial in E of t. So actually, we consider the polynomial P of t as an element of E of t, which is, so here we're thinking of these elements, right, which are in F, as elements of E. And so we can either just mentally think of that, but since we're actually calling the elements of E that correspond to F with these brackets, let's use that notation, right? So now we have this. Okay, let's use the original color. Okay, now I want to show that if we set, so we want to show that this has a root in E. Now, I claim that if we set the cos t to be equal to the coset of x, we claim that this is the root of P of t. Okay, now this is an element of E, right? Because the elements of E are precisely the cosets of polynomials in F. Okay, which this is. So the proof goes, okay, well, if you substitute it in, what do you get? You get this plus this times this plus this times this squared plus dot 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 plus this times that to the nth power. Now remember how we defined the field. How did we define the operations of a field, the addition and multiplication here? Let's just recall that the way we defined it is that we define, if you have the coset of g times the coset of h, that's defined to be the coset of g of x times h of x, right? And you also define the addition by this property, that you add two cosets by just adding the elements in each coset and then checking that that's well defined. So that's the operation. And so therefore this is equal to, okay, so you have the coset of a naught, and then we defined this, right, to be the coset of a1x. a1 times x. And we defined this thing to be the coset of a2 times the coset of x squared, which is precisely the coset of a2x squared, and all the way down to this. And so this is equal to the coset of a naught plus the coset of a1x plus the coset of a2x squared plus dot 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 plus the coset of a n x to the n, right? And by definition of the addition, so this is by the addition, the definition of multiplication in E, and then this sum is equal to the coset of this polynomial by definition of the addition in E. Now what is this coset? Well, this polynomial is precisely p of x. So it's the coset containing p of x. Okay, but the coset containing p of x is just the coset containing 0. And so this is the 0 element in E. And that completes the proof. We just showed that when you plug in this thing in for t, you get the 0 element of E, which is the coset containing p of x. And that completes the proof of the theorem. So this is, pretty abstract. So if you look at a specific example, this example is somehow not general enough, but let's just do it anyway. If you take f to be r, we can consider the polynomial p of t equals t squared plus 1. That's irreducible in R, and you can define E then to be the quotient ring, the quotient field, R of t mod the ideal generated, or okay, R of x if you want, mod the ideal generated by x squared plus 1. And then this is going to be, since this is up to equivalence, you can think of this as cosets of a naught plus a1t, right, or a1x. This is it's this as a set, but then there's this weird multiplication rule, and then and the coset x so with x satisfying x squared plus 1 equals 0. And so you can think of this as the complex numbers, right? And it is in fact true that whenever you have a polynomial with real coefficients, it has a complex root. Let's see, I think I'm being a bit sloppy with the notation here, but this is essentially the idea, to make this construction a bit more concrete. Okay. Okay, thanks for watching.